Hey, what's up everyone, it's Zain. I'm going to be making a video on recurrence relations. So let's get started. Let's do it. So it seems like a lot of people still have trouble with recurrence relations. Like I've done, at this point, a couple of videos on recurrence relations, how they work. But I'm gonna make sure to explain like the thought process of how I do it and how you can easily solve any of these. Actually, this is probably one of the more tedious ones, so I'm going to start off with an easier one, and then we'll end up going back to this one. This one as well. I'm going to go with a different one. Okay, let's do, for example, this one. So this one right here, first thing to notice, whenever you go to these, we're just doing iteration technique, solve in terms of n, given exact closed form instead of big O. So we're doing closed form in terms of n, and they give us this recurrence relation. Notice that the recurrence relation is based on n minus 1, so we're not doing any sort of division. We're not dealing with powers here. That's the first thing to notice. So this is going to work a little differently than normally, but these are actually way easier. So let's just end up starting it off. So t of n, 3t of n minus 1, and we have our plus 1 for all n greater than 1, and we have our base case t of 1 equals 1. Okay. Also, they say the useful summation formula for this question is the following. So this is the formula, the famous formula. I told everyone, write this down, because this is one of the few questions that they'll actually give it to you, but most of the time they don't actually end up giving it to you. And a lot of times it can save you if you don't really know what to do, because you have some sort of something to the power in a summation. So first things first, let's do our 3 iterations. The 3 iterations are easy. It's just algebra. First thing, let's notice the structure of the recurrence. This term on the side of the the recursive calls in this expression, this has no n, meaning we're not going to have to change anything as we go through the recursive calls based on this, because sometimes if this was, for example, plus n, then in the next recursive call we would end up doing n minus 1 right here. So we would have, for example, n minus 1. In the next recursive call, we would end up doing n minus 2, because we would have something like t of n minus 2, etc. But in this case, we're not going to end up doing that. We have a constant, so this is how we're going to end up going about it. So first things first, I've done this before, but I'm just going to do it real quick. Let's set this as a sort of variable, right? So this is going to be equal to the next iteration. So 3t of n minus 2 plus 1. So that's what it's going to be whenever it's like there's no plus n or something like that. So it's just going to be plus 1, and the only thing that's really going to change is this in these type of like linear kind of what do you call it, recurrences. And I'm not saying that the final answer is going to be linear. I'm just saying that in this case, we're doing like n minus 1, n minus 1, n minus 1, etc. So n minus 1, n minus 2. So it's not necessarily going n divided by 3 to the k, n divided by 2 to the k. We're not dividing every single time. We're just going minus 1, minus 1, minus 1. So I'm just going to keep going. I'm going to plug in what the next iteration would be based on this. So I like to write the constant term, write brackets for what we're going to add in here, and then write this. This is what I call this piece right here, the summation terms. So this is going to end up building a nice summation you can end up seeing and piecing back together. And you can use this, you're going to use it to create your final answer. But so now at this point, we've written on the constant, put our brackets, and we've also accounted for this on the outside, the trailing summation terms. Now let's just plug in what we know this is going to be. So it's going to be 3t of n minus 2 plus 1, and let's distribute everything out. So now we're going to have 9t of n minus 2 plus 3 plus 1. So let's note, this is our summation terms that are getting built out. So now we have a 1 and a 3. But instead of adding this 3 here, what I like to do personally, I would, or actually, let's not do that right now. I'll do that step later. So let's just keep going from this. We're going to do another iteration. So same setup, write the constant term, put our brackets, and add the trailing summation, and plug in what we know it's going to be. Okay, now we're just going to distribute. Okay, and now at this point, we've done our 3 iterations. So now this is where we're going to try and find the general form. And the general form is pretty much how we see things are changing as we go through the iterations. So first things first, what I always like to do is deal with these terms here, because this is going to kind of, set the tone, because people tend to have trouble putting things in terms of like summations, but I'll show you guys how you can do that easily. So this is third iteration. Let's write first, second iteration. Okay. So now right here, what I like to do is order these based on what was determined in the first iteration, what we got in the second iteration, and what we got in the third iteration. So notice how our first iteration, we had just 1. In our second, we added a 3. And in the third, we added a 9. So now let's just put that in order of how we got them, right? So now this is going to become 1 plus 3. And you don't have to put this plus here. I'm just doing it, just to make it easier to see. 1 plus 3 plus 9. So now let's think, okay, how are these values changing based on the order in which we got them? Went from 1. How do we go from 1 to 3? By multiplying 3. From 3 to 9 by multiplying 3. So clearly, each term is getting 3 times bigger, which with every recursive call, every iteration. So now from this point, you can say, okay, we know that the first term is 1. If every time we're multiplying times 3, that means we're kind of like, we're gonna end up having some sort of summation where each term is some sort of power of 3, right? So we can say this could be, for example, 3 to the I. But if we notice what can we put to any number to what power will give us a 0? For any number you put a power of 0 to, it'll give you a 1. But I think I might have said that wrong. But yeah, what I meant to say, any number that you put to a power of 0, it will give you 1. Doesn't matter what the number is. So you know that since this was the first term you had, your summation is going to have to start at 0, because if you have something like this, which is how this is changing, iteration 1, you had a 1, then you had a 3, so that's 3 to the 1. This was 3 to the 0, and this is 3 to the 2. You know 2 things from this right here. You know that since this is a 1, the only way you can get that from 3 to the power of something would have to be if it started at 0. Remember, summations, okay, I'm not sure what that is, but remember that summations, they go from whatever this term is upwards up until a certain number doing, whatever it's summing in here, right? So meaning let's just see what is the first term and what is the last term, like what this I is going to be. The first term obviously is 0. The second term is obviously 2 right here. So we see 3 to the 0. And then the last term we had a third iteration was 9. So that's 3 to the 2, right? So this is going to be very important. We know that we're going to end up in the third iteration. We're going to end up going from 0. So we're starting at 0. We know this is based on 3 to the I, but we don't know what our top bound is. And this is how we're going to figure out what our top bound is based on, the information we have. So at this point, when you're going to determine what your top bound is, you're going to need two pieces of information. You're going to need to know what is the last iteration right here, right? Like what the last power is of this term. And you're also going to need to know what the what k currently is. So I'll show you how to figure that out. So this is where I like to go to the very first iteration, right? So you can go from the first or you can go from the end. I think it makes more sense if you start from the first. So this is 3 to the 1, right? And this term right here is currently 1 in iteration 1. In iteration 2, this is 3 to the 2, and this is 2, right? In this iteration right here, this is 3 to the 3, and this is 3, right? So we know that this, by the way, is going to be our k. This term to the 2, to the then minus 2, to the 3, minus 3. That is going to be our k. And now by knowing our k, which is one of the main difficulties of recurrence relation, now we can actually produce a general form solution, or not necessarily a solution, but a general form which pretty much tells us the trend of how things are changing. We're going to use this information that we just found out to see why we can find the top bound of the summation now. So notice it's 3 to 3, and then we have a minus 3, right? So we know that at the third iteration, k is equal to 3, right? So we can use this information to see, okay, if k is equal to 3, how does that relate to the this summation? At what point did the summation stop? And that will give us our top bound. So notice k equals 3, right? We know that. We know that the last iteration was 2. So last I equals 2. So what we can do to find what the top bound is, it's literally just 3. We just try to do something like this. Set 3 equal to 2. What do we have to do to change 3 to go down to 2? Minus 1. So remember, 3 is k. So this is really k minus 1 equals 2. And notice how that is the last iteration we're going to be doing. So what that means, the last iteration of our summation is going to be equivalent to k minus 1. And k minus 1 is what's changing, like k is what's changing through the iterations. And that's going to tell us at every given iteration what the summation is going to go up until. So now this is just going to be k minus 1. Now let me explain, and I guess kind of like in a way, kind of prove lightly how you can tell this is the case. So it goes up to k minus 1. You're like, okay, so k is 3, k minus 1 is going to be 2. This summation stops at 2. Okay, that checks out. This is currently in iteration 3. Let's go up to iteration 2 and see if this holds. Because if it works in 3, it should work in 2, right? So right here, we have k equals 2. And notice how if we reorder these terms, we're going to end up having plus 1 plus 3. This right here is 3 to the 0. This right here is 3 to the 1. So 3 to the 1. What is our k? Our k is 2. How can we get from 2 to 1? Subtract 1. That means that this is running from k minus 1, meaning 2 minus 1, and then it starts at 0 because we know that's our first term. That's how we get 1 from 3 to the power of something. So it's still holding. The same property still holds. So that's how you can check your work. And even in the first iteration, it still holds. But I'm not going to show you guys that. Okay, so now we know how we can do that. I'm just explaining it to you guys. But now we have our summation. And from this point, we can work with the rest of this right here, right? So we know that, let's establish our general form now. Now at this point, we know that this term is something to the power of k, so 3 to the k, and then we have times t of n minus k plus the summation, right? So this is our general form right here. And now we can start solving. So let's look at our base case. Our base case is t of 1 equals 1. So what we're going to do, we're going to set what's t of 1, just set the 1, and then what's in here equal to each other. So t of 1 equals t of n minus 1. Set these two things equal to each other. So that means we're going to have n equals k minus 1, or k plus 1. And also we know that k is going to equal n minus 1, right? Okay, so that's good. Now let's just plug away. So 3 to the k, we know that k is going to be equal to n minus 1, right? Now we have this term times t of, and let's just plug in, what can we plug in to make it easy? Yeah, let's just plug in n, or let's just plug in k, because that's what people normally do. n minus 1. I got that from here. So we distribute this. Or actually, did I? Yeah. So we're good. And we distribute this. We're going to end up with n minus n plus 1. So it just becomes 1. And then we have t of 1. Remember, t of 1 is equal to 1. So that means this entire thing is just times 1. And anything times 1 is just itself. So we can remove that. Now we're going to have plus k minus 1, right? So we have k minus 1. But guess what? We have an n. So we can just remove that. K minus 1. If k is equal to n minus 1, and we had k minus 1, this is really going to be equal to n minus 1 minus 1. So we're going to plug in n minus 1 minus 1, which is just n minus 2. Okay, now we have 3i. I equals 0, right? So right here, this is one of those questions that people tend to, it doesn't really make sense, but trust me, it does make sense. Really, what's going to end up happening here is you're going to merge these two, this term into the summation, and the final answer, or not necessarily the final, but up as you get to the final answer, you're going to end up having something like this. So this is where you're going to go to from this point. But let me explain why that is. So notice how we have a summation, right? So it starts at 0, goes up until n minus 2. So that means we're going to have 3 to the 0 plus 3 to the 1 plus 3 to the 2. Then eventually we're going to have a plus. Then we're going to have 3 to the n minus 3 plus 3 to the n minus 2, which is going to be this last term, right? Because this is inclusive. So the way it works is that this is a summation. And if we add a term 3 to the n minus 1, this is actually the next term in the sequence if we keep going with the summation. So that means we just go up by 1. So now we're going to end up, like we just end up adding it, and that means we're just extending the top bound a little bit longer, right? Because it's still following the same trend. It's still 3 to the power of something, and this and n minus 1 just happens to be 1, the next term in this sequence, if it was n minus up until n minus 1. So that's how they end up merging it. So a way I like to explain it is, let's say you have something like 6 plus 5 I equals 1 of I. So of course, this is just going to end up being equal to 6 plus 1 plus 2 plus 3 plus 4 plus 5. But if you think about it, since math, or not math, but addition is commutative, you can just do 1 plus 2 plus 3 plus 4 plus 5. And let's just put this here for easy, so it looks easier, right? Or it looks more like a summation. 1 plus 2 plus 3 plus 4 plus 5. That is the same exact thing as if we just had a top bound of 6, starting from 1 or 0. It actually doesn't matter, but in this case, and that's that. So it ends up coming out to the same exact answer. It's just, you just merge the two. Another way I explained it to somebody was, let's say you had something a little different. And by the way, you can extend upwards and you can extend downwards. So what I mean by that is, let's say you had I equals 2 to 5. And let's say you had it had I inside the summation, and then you did you know what, let's make it a little more difficult to see. So let's say you do plus 9. Okay. Or actually, let's select this. The 3, that's what I meant. So it's going to be, yeah, okay. So plus 9. What is this really equivalent to? Believe it or not, this is actually equal to, if you merge it together. And this is kind of like, they're probably not going to ask you something like this, but this is a little more, I guess, creative you have to be. But let's think about it. And really, this would also work if this is 0 as well. But let's think about it real quick. So in this case, we have a summation 3 plus 4 plus 5, right? And then we have 8 plus 9. But let's think about it. How many ways can we get 9? So we can add a bunch of ones, right? Eventually we'll get to 9. We can add 1, 1. We can end up adding 1, 8. We can end up adding 1, 1, 1, 7, 1, 1, etc. But if we think about terms that can compose 9, we can think of, for example, plus 1, or we can think of plus 3 and plus 6, right? So now we have 3 plus 6 plus 3 plus 4 plus 5. And you might be like, okay, so like, how does that help me at all? What if I could order them a little differently? So we did plus 3 plus 3 plus 4 plus 5 plus 6. So now at this point, you're like, okay, so it looks like there might be something going on here. But you see this 3, so you're like, okay, what can I do here? If you think about it, to get to 3, you can do 1 plus 2. So you end up with 1 plus 2 plus 3 plus 4 plus 5 plus 6. So that is why this right here actually ends up equaling this. Because if you move the numbers around, or if you think about it a little differently, then you can end up adding it into that. And what I ended up doing, this one was kind of weird. I ended up increasing the top bound and decreasing the bottom bound by adding terms that would belong there, all the terms that would belong there. So that's a little, insight into how they're going about it and thinking about it. I hope that made sense. But yeah, back to this. So yeah, you just end up merging it because this is the next term in the sequence if you keep going up. And from this point, we're just gonna plug in the formula. So again, this is a famous formula. Just write it down. It's gonna be 3 to the, remember, n is just whatever's here. N minus 1 plus 1 minus 1 all over 3 minus 1 is going to be equal to 3n minus 1 all over 2. And that is our final answer. So let's check. So yep, final answer. There we go. So I hope that made sense. All right, so let's go on to the next one. And now we're going to try and do this one quick. Let's do this one a little quick. Okay. So let's just write all this information down. This is going to be a little different. We're dividing by 2. And we're just going to follow the same steps that I mentioned. This is going to be a little different because we have an n sort of term. Okay. So whenever they give you this kind of stuff, whenever you see that term that they tell you about, just plug it in. Just don't think about it too much and just do it. It'll end up giving you the answer eventually. Because there's some stuff that they do just to make it easier for students. Kind of like they have calculus-based reasonings why they do it, but yeah, you don't have to worry about that. It's not a calc class. Okay, so let's start off. First things first, we notice we're dividing by 2, so this term is going to be increasing as a power of 2. So 2 divided by 2, you can think that that is n over 2 to the 2, then 2 to the 3, etc., etc. And right here we have an n term. So really, in the next iteration, we're going to have whatever was here and divided by 2, and then we're going to square that. Then in the next iteration, we're going to end up having what was here, which would be n over 4, and then we're going to square that. So that's going to be like the whole template for this. So let's just go through it and you can see. Okay, first things first, do our 3 iterations, right? The constant, the brackets, 3t, account for the next iteration, divided by 4, plus, now remember what I had mentioned, put what was here into here, and then square it. Oh yeah, and also I always mention, I didn't do it this time, but add these terms first, so you don't forget about them. Now let's distribute everything. Okay, so now we did 1 iteration, let's go again. Bubble was in here for n squared. Oh yeah, I also did it again, but write this first. These are your summation terms. Very important you don't mess it up or forget them. And let's end up distributing. Okay, so now let's order these terms, the summation terms, in the order that we found them. N squared, 3 over 4 n squared, 9 over 16 n squared. So now we're going to have n squared, which is 1 over 1, plus 3 over 4 n squared, plus 9 over 16 n squared. Now from this one, we have a constant term of n squared in all of them. So let's just pull that out. 1 over 1 plus 3 over 4 plus 9 over 16. Okay, so there we go. So now what's going to happen, let's notice what iteration term we're going to be on. But first, before we do that, let's see how things are changing. So we did times 3, times 4, times 3, times 4. So at every iteration, we're changing by 3 to the 4. So that means our summation term is going to be this, right? So this is iteration 0, because that's how you get 1 over 1 if you put this to the power of something. This is obviously 1, and then this is if you square it, so I equals 2, right? And yeah, so now we have this part established. We see like what it's kind of going by. So we're going to have n squared. Now let's just write out the summation because we already know it's a summation. So 3 over 4 to the I We don't know top bound yet, but we'll figure that out. And I equals 0 because we know we have a 1/1 term. Now let's look at the rest so we can establish our general form. So let's see how things are changing. So we started off with 3, just 3/1, or 3 to the power 1, and 2 to the power 1. We ended up with 3 to the power of 2, and we ended up with 2 to the power of 2. Then we had next iteration, 3 to the power of 3, 2 to the power of 3. So we notice k is currently 3 at the third iteration. Iteration 2, k equals 2. Iteration 1, k equals 1. Right? So, with the same steps that we did in the first question, we can see that where does this summation end? It ends when I equals 2. If k is currently 3, the only way to get from 3 to 2 is by subtracting 1. Therefore, our top bound is k minus 1. And let's do a plus. And let's establish what these are. So this is just 3 to the k times t of n over 2 to the k. And that's that. So this is our general form. This was the hard part. Now, whenever they give you one of those infinite summations, it's because whenever you have something that's almost identical to this, but the top bound is not the same, they just want you to replace it with that infinity, right? And yeah, it's going to end up converging. And you just set this equal to whatever they told you. So they told us it was 4. So let's just put our 4 here. So this is what we're working with, right? What's our base case? Our base case was t of 1 equals 1. So we're going to set t of 1 equal to what's inside of here, which is we're going to have 1 equals to n over 2 to the k. That means we have 2 to the k equals n. Then we're going to have, we just write it in terms of k equals log base 2 of n. And now let's plug away. We're going to have 3 to log base 2, or actually it was like, it's going to be 3 to the log base 2 of n times 1 plus 4n squared. This right here is going to be, I believe they said it was n to the log base 3 of 2 plus 4n squared. And now, remember, they gave us this information. They said log base 2 to the log base 2 of 3 is less than 2. So let's think about what is the dominating term. If we know that log base 3 of 2 is less than 2, notice we have a 2 and then we have this right here. So they kind of tell us what the answer is at this stage. Then all we can do is just write an n, because these are the terms we have. And we know that, okay, if this is something in the range to exclusive to, I guess it can be really anything, you could say. If it's in this, then it's not, it's going to be less than 2. So if it's less than 2, that means 2 is a dominating term, and therefore our big O is just going to be n squared. That's it. So that's our final answer, n squared. So let's check it out. Yep, so that's it. That's exactly it. So yeah, like I said, I always recommend just doing, those steps that I mentioned. Now, this one is probably going to be a little more annoying, you could say, but let's end up doing it real quick. So t of 2t of n minus 1 plus 2n. I'm going to follow the same steps I've been doing. T of 0 equals 1. Let me just see real quick what it says it is. Okay, perfect. For all integers less than or equal to 1. I mean, we don't really care about that, honestly, but why not? Let's write it. Okay, so now we're going to do the same iterations we've always done. But now we're just going to pass, remember how we were doing whatever term was here? We're going to plug in if we had an n squared. Now we're just going to plug that in for this right here in the next iteration. So that's the whole process. So let's just start doing it. Write this, write our summation terms, don't forget it. And now let's do this inside of here. 2t of n minus 1 plus 2 of n minus 1. So now we're going to have, let's just distribute this over. So we're going to have 4 t of n minus 2. And this one, I'm not going to necessarily distribute over. I'm just going to leave it. So we're going to have 2. Remember, 2 is just 2 to the 1 times 2 to the n minus 1 plus 2 to the n. Now right here, what's going to end up happening is we're going to do again. So we're going to have 4. Give us ourselves space and write the summation terms. So this is the trailing summation terms. And now we're going to write 2t of n minus 3 plus t of n minus 2. Just transfer it over, that's it. Now let's just do the algebra. And again, in this case, I'm just going to leave it how it is so you guys can see my thought process on this as I solve it out. So times 4, let's just put this in terms of powers of 2. So 2 to the 2, they're just going to end up being, actually, let's just keep it in terms of 4 real quick. So it's just 2 to the n minus 2 plus all of these terms right here. So now we've done 3 iterations. Let's see what we can end up doing with these summation terms. So we know that all of these summation terms, there's probably some sort of trend. There's always a trend. You're always summing something somehow. So 4, like I said before, 2 to the 2. Remember, whenever you have something of the same base, but with an exponent, let's say x, times something, same base, exponent y. And by the way, y can equal x. That is perfectly fine. Then what's going to end up happening is going to become b to the power of x plus y. That's fine. So let's just end up distributing this over. That means we're going to have 2 to the power of n minus 2 plus 2. There's going to be, actually, let's just keep going. 2 to the power of 2 to the n minus 1 plus 1. Then we're going to have plus 2 to the plus 2 to the n. And by the way, this, you can think of this kind of like, let's think of it like this. Plus 2 to the 0 times 2 to the n, because remember, it's just going to be n plus 0. So 2 to the n. And right here, we're going to have 2 to the n plus 2 to the n plus 2 to the n, right? Okay, so far, so good. This is what we're working with. This is our summation term. So let's just think about how many iterations we've done so far. So far with every iteration, we actually end up removing, you know, all these constants in front of these numbers that we're multiplying against. So we just end up with the same thing being added, a certain number of times. So we added it 3 times, and let's find out what our k is. Right here, this is 2 to the 3, this is 3, this is 2 to the 2, this is also 2, this is 2 to the 1, this is 1, right? So now from here, if this is 3, and let's see up here. So this right here, we just added 1. So really, we can just say it starts at 1. It doesn't really matter. We can either start at 1 or we can start at 0. I'm just going to go ahead and say it started at 1, because then we can use some formulas, but it doesn't really matter. So say it starts at 1. This is really going up until k, and this is going to be equal to 2 to the n. Now from here, we're just going to end up solving this part out in general form. So we're going to have 2 to the k times t of n minus k, right? So that checks out. Now from here, we're just going to go back all the way up, see what they gave us. T of 0 equals 1. T of 0 equals 1, so we're going to have n minus k equals 0. That means n equals k, k equals n. So now we're going to have, let's plug in, try to remove the k. 2 to the n, and then this is going to be equal to 1 plus, let's plug in n at the top, 2 to the n, I equals 1. Now remember, n has to be some sort of finite value. So there's 2 ways of thinking about this. You can end up pulling this value out. That would make it something like 2 to the n of I equals 1. And then this right here is going to be equal to 1. And then from here, you can do the formula for constants, where it's C of B minus A plus 1, right? Or alternatively, you don't even have to, bring it out and then do it based on 1, because now you're going to have 1 times n minus 1 plus 1. And then it's going to be equal to n, then times 2n. What you could have just ended up doing, since you know that 2n is a constant, since n has to be finite, since that's what your summation is going to be bounded by, then, and it's really, that's what you're passing in, it's going to have to end at some point, then you could just plug it into that formula directly. So you can just literally have this right here. You're going to have C, which is just 2 to the n, times n minus 1, so B minus A plus 1, cross this out, then we have 2 to the n plus n times 2 to the n. And think about it, what can we factor out? We can factor out a 2 to the n. Now we have n plus 1, and this is our final answer. So let's see, 2 to the n times n plus 1. Two to the n times n plus 1. So that is the whole idea with the way I end up doing this. Let's do one last question. So big O solution to 3 iterations followed by general form and complete the solution. So 2 t of n divided by 2 plus n squared t of 1 equals 1. Okay. So I think this was it. Yes. Okay. So yeah, this is not an n right here. Okay, so same formula. First iteration, let's write our trailing summation. 2t of n divided by 4. And then plug this in right here for the n squared. So n divided by 2 squared. Now we distribute 4t of n divided by 4 plus 2 over 4 n squared plus n squared. This is our trailing summation we're building. Now let's go again. 4 of 2t of n divided by 8 plus, plug this term in for the n squared, n over 4 now remember trailing summation. I forgot to write that first. And now at this point, we're done with our summations. It's going to be 4 over 16 n squared plus 2 over 4 n squared plus n squared. Okay, so now what we always do, if we have a constant term like an n or n squared, pull it out of all these because they all have it. Now just order them in terms of how you got them. So this is really just 1 over 1. So we start off with 1 over 1 in the first iteration. Then we got 2 over 4, and then we got 4 over 16. So really this is 1 over 1. 2 divided by 4, it's going to give you 1/2 plus, and 4 over 16 is just 1/4. Right, so now we can see what the trend is. This just stays times 1. This just stays times 1. This right here goes times 2. This goes times 2, right? So really what ends up happening is we're doing something like this. Again, for a term of anything to start at 1, other than it being 1 itself, clearly it's 1/2. And we just have to start at I equals 0, then I equals 1, and then I equals 2, right? So our last term, first term, this is important, as you guys know. So now let's start writing our summation. We have n squared times summation of 1/2 to the power of I equals 0. We don't know what our top bound is, but let's just look at the rest of the recurrence and we'll get it. 8 is, okay, first of all, what do we start off with? 2. So 8 is 2 to the 3. This is 2 to the 3 as well. Second iteration, we were 2 to the 2, 2 to the 2. First iteration, we were 2 to the 1, 2 to the 1. Okay, so in this iteration, k is equal to 3. Our last iteration was up until I equals 2. So guess what? Again, k minus 1, right? And I don't think they give us a formula here, but by the way, the formula for when they give you these is really just, so the way I like to look at it is, or this is really like a calc thing. This is an I, this is an N. The way I like to think of it is just A over 1 minus R. So A is just a term that you multiply, and then this right here would just be, actually, let me just do it like this. So in these examples, A is always going to be 1. So really, it's just 1 over 1 minus R. R is what changes in these examples. They don't expect you to, know this. But yeah, this, you're just going to do 1 minus R. R is going to be equal to 1/2. So it's going to be 1 over 1 minus 1/2. This is going to be 1 over 1/2. And this will just give you 2. So that means this entire summation right here is going to be equal to 2. By the way, this formula is on the test. on the formula sheet, so you will get this. So let's just rewrite this as a infinite. Remember, whenever this term is less than, whenever this term right here is less than 1, then you're just going to convert it to infinite. Use that formula I mentioned. And like we saw, this is equal to 2. So we're just going to have 2. And now let's bring down the rest of this, the recurrence for our general form. So there's going to be 2 to the k t times t of n over 2 to the k, right? And then now let's just solve. So what is the base case? It's t of 1 equals 1. So we're just going to do 1 equals n over 2 to the k. Solve for both. Okay, done. And now this one, let's just plug away. So we have n times, there's going to end up being 1 plus, and we have 2n squared. And I don't remember what they were asking us for. It was the big O. Okay, big O. So we have 2n squared plus n. This is really just n to the 1. What's bigger? N to the 2 is great. I mean, yeah, n squared is greater than n1. So our answer is just going to be 12n squared. So that's that. So let's check our answer. Yep, so same idea. That's pretty much how I do my recurrence relations. I hope that helped everyone, because I know this is one of those things that are like, it's very hard for people to like, answer and all that sort of stuff. But yeah, I hope this made it look not as bad. After you look at it this way, track your summation terms, write order them in the order that you got them. Pull out a constant, and then after you've done this, go straight to how these numbers are changing. Easy. Get your general form, solve for these couple variables, and after that, that's it. Just notice after you get to the correct general form, everything is easy. So, for example, I got here, then it was just a couple of things. That was it. Let's see, what was this other one? Yeah, right here. Got to this form, same thing, did this, done. So that's pretty much about it. Yeah, there we go. Anyway, everyone, I hope this helped you guys understand recurrence relation better, pass, CS1 test, foundation exam, whatever it is you're using this video for. So yeah, good luck. Peace.